Hi, everybody. I hope everybody is doing well. This will be our first lesson of new physics stuff since we haven't been in school due to the coronavirus. I hope everybody's staying healthy, staying well, and also trying to stay upbeat. I know it's not always easy being stuck in your house, but we're all in it together. We'll get through it, and just got to do what we got to do. Um, Okay, so our first lesson that we're going to talk about, this next unit that we're moving into is energy. And what we're going to talk about today is just some really basic stuff. What it is, the types of energy that we are, some types of energy, I just should say, just some of them, and transformations of energy. Okay, so what is energy? The definition of energy is pretty vague. It's what it is. Energy is the ability to do work. The way you can think about that is that it can cause a change in another object, right? So, for example, everybody remembers what happened to me back at the beginning of the school year. So, like in a car accident, right? So, if a car's driving down the road, it has energy because it has the ability to cause a change in another object, maybe, another car. So car while it's driving, if it hits another car, can change that what's going on with that other car, obviously. Okay, so that's what energy is. Energy is the ability to do work, which means that all that means is that it can cause a change in something else. So next thing we're going to talk about is different types of energy. I'm just going to make a quick list here. We will talk about mostly is a little bit more, but just to throw them all out there. So one type of energy is thermal. Another one is chemical. Another type of energy is nuclear. Another type is electrical. And we also have light, sound, kinetic, and potential. Different kinds of energy. There's lots of different kinds. Okay. The interesting thing is that most energy that we regularly use as humans ultimately comes from the sun, right? So, well, what happens? The sun sends its light and its heat, and the sun feeds plants, right? And then plants feed animals. And both of those things, animals and plants, they feed us. And then when we eat those things, our body breaks it down, turns it into chemical energy, and then that energy goes to actually the next thing that happens is how does our brain work? Our brain works through electrical signals, electrical impulses, really, really small, just pulses of electricity is what makes like your arms move. Your neurons in your brain send a small pulse of electricity down to your muscles when you want to move your arm. Okay. And then when you move your arm, that's moving, that's kinetic energy. We'll get more into that. Okay. But where did that, right? So there's a chain of energy went from this place to this place to this place to this place, on and on down the line, right? But where did it ultimately start? The sun. And even if you think of like something like, okay, what about gasoline, Mr. Christopher? How does that come from the sun? Well, a lot of oil comes from deep in the ground, and what oil is it's the remains of dinosaurs that has chemically broken down over a long time. And so, what did the dinosaurs eat? Each other and plants. And where did those things get their energy? The sun. Same. It's so. I don't want to make a blanket statement and say everything, but most of the energy that we use in our regular lives as humans, ultimately, you can trace it back to the sun somehow. All right. So, quick couple different kinds of energy here. We won't spend a whole lot of time on these. Thermal energy is one kind of energy we put on our list there. It's related to temperature and heat. Temperature and heat, that's thermal energy. Higher temperatures mean more thermal energy. Okay, so, and if obviously, then if you cool something down, that means it's losing thermal energy. Nuclear energy is the energy stored in holding together an atom. Remember the atom here? We talked about that in chemistry. Talked about that at the beginning of this year. You've got your protons and your neutrons there in the center, in the middle, electrons flying around the outside. Well, there is energy holding that together, right? If you break apart an atom, very catastrophic things happen. There's an entire bomb designed around breaking apart an atom. It's called the atomic bomb. It's the one that the United States used against Japan in World War II back in the 1940s. So very simple little atom here, but if you manage to break it apart into two pieces, very crazy things happen, right? That's a lot. And there's actually a lot of energy, and if you can break it apart, that's a lot of. It causes a lot of damage, obviously. Okay, some more types of energy here. Chemical energy. Chemical energy is energy stored in holding together atoms that make up a compound, like water, right? So you've got two hydrogens bonded to oxygen, and that's water. And so bonding, there's energy involved in bonding. Now, the interesting thing is actually if you break the hydrogen off of the oxygen, you don't get energy by breaking them apart. It takes energy to break them apart. Things like to be in a lowest energy state, and it's actually lower energy for those things to be stuck together than it is for them to be separate from one another. Okay, so the way if you wanted to use chemicals to convert some energy, you would actually want to put things together, not break them apart, to get energy out of it. We also have sound. All sound has energy. The amount of energy a sound wave has is related to the volume or the intensity of the sound. So the louder it is, the more energy it has. Really, really simple. Louder sounds have more energy than quiet sounds. Light also has energy. All light does. All sound and all light, they do have energy all the time, every single time. If there's sound, there's energy there. If there's light, there's energy there. Light energy, actually, it's really interesting. The amount of energy that says sound wave. That should say light. We'll just right over that. That should say light. Okay, the amount of energy that a light wave has is actually related to the wavelength. So color. So lights of different color have different energy. So if you have a red light bulb and a green light bulb, the light coming from those bulbs has different energy because they're different colors, and that means they have different wavelengths. So that's how light breaks down, is it's based on the wavelength, which pretty much means the amount of energy a light wave has is based on the color. All right, the next thing we want to talk about here is kinetic energy. This is one of the two kinds of energy that we're going to be spending quite a bit of time on in these units. So this one's pretty important, which is why I put it here towards the end. We can focus on it here. Kinetic energy is the type of energy related to motion. Any object at all that is in motion, if it's moving at all, then it has kinetic energy. Okay, anything moving has kinetic energy. It depends on the speed. So going faster means more kinetic energy. And it also depends on the mass. More mass also means more kinetic energy. All right, so the last one that we're going to talk about is potential energy. This one is probably by far the strangest, hardest to understand, but it just can be a little bit tricky. But I'm sure you can grasp it. You'll do fine. So potential energy, very generally, is energy that is stored in some sort of way, which means chemical energy is a kind of potential energy, right? It's energy that's stored in the bonds. And then we also have nuclear. That's a kind of potential energy. We also have spring and gravitational. The one that we're going to be most concerned about is gravitational, which we'll talk about on the next slide. But I'm going to use the spring version of potential energy to kind of introduce what this is all about. Okay, so let's do that. Let's first explore spring potential energy. Okay, so we're just going to kind of walk through a mini experiment in our head. We're not actually going to do it. We're just going to imagine it. Okay, but it's nothing crazy. So here's what we got. We have a spring that's attached to the wall. So here's our spring, this zigzaggy thing. It's attached to the wall, and it's pretty close to the floor. Okay, so this is our setup. We got spring that's attached to the wall. Okay, so here's what we're going to do. We're going to push a box up against that spring. Here's our blue box, and it's on the floor. And we push that box up against the spring and we squish it. Or another way to say it is compress it. So we're going to compress that spring with this box, and we're going to hold it there. So it's just sitting there right now. The spring is squeezed. The box isn't doing anything. Okay, we're holding it there. Nothing's moving. So because nothing's moving right now, some might say, well, there's no energy then. Nothing's moving. So since nothing's moving, there's no energy. But what happens if we let go? Right? We're the one that's holding the block against the spring. What's going to happen if we let go? Well, the spring is going to push on the box, right? That's how springs work. If you take a spring and try and squish it, it pushes back on you. Okay? So when you let go, the spring is going to push on the box, and that means that and then the box is going to slide across the floor, kind of like this. Here's the spring, kind of like a pinball machine, right? If you ever played a pinball machine, the little pinball falls down there. You pull the spring to compress it, and then when you let go, it shoots the pinball into the machine, and then you play pinball, right? And so that's exactly what's going to happen here. The spring is going to push the box across the floor, and then it goes back to normal. So the spring had stored potential energy. This is where we get into the potential energy part of it. We did this little experiment. We saw what happened. Here's the big conclusion, right? The spring had some stored potential energy. And we know that because this is energy that it could have used to push the box away, right? Right here in the middle of this experiment, it wanted to push the box away, but we were holding it back, right? So it could push the box, and it will push the box once we let it go. We were holding on to it to keep it still. Once we let it go, then that spring is going to push out and push that box across the floor. So it had energy, and it was waiting. It could not use it until we let it go. But so before we let it go, that's stored energy. So that because it's stored, that's potential energy. So that's potential energy that's stored in the spring until we let go. So let's try and think of what that means for gravitational potential energy. This is that. I mentioned that there's two kinds of energy that we're going to focus a lot on. The first one was kinetic. Here's the second one, gravitational potential energy. Okay, so this is energy stored in gravity. And the one we just did, that energy was stored in a spring. This time we're storing energy in gravity. And you're like, well, how can you do that? That doesn't make a whole lot of sense. Well, it's not hard to do, but we'll get to that in a second. So let's remember that the one we just did, the spring can and will push the box, right? But not until we let it go. Gravity works the same way. So imagine you hold a water balloon above the ground off the top of the school bleachers, right? Gravity can and will cause the balloon to speed up towards the ground, but not until you drop it, right? As long as you're holding it there, it won't move. But once you let it go, gravity can and will cause the balloon to speed up. Okay, so that's energy that's stored, and it can't go anywhere until you let go. This time, instead of energy being stored in a spring that we have to let go, we're storing energy in the fact that we're just holding the balloon above the ground. Gravity wants to pull it down, but we're holding it, so we're not letting it go. Gravity can and will make the balloon move just like the spring, but not until we let go. So that's energy this time that's stored in gravity. Okay, gravitational energy depends on height. The higher an object is off the ground, then the more gravitational potential energy it has. It also depends on mass, just like kinetic energy. More mass means more energy. So mass is the one thing that goes into both. Mass goes into potential energy, and mass goes into kinetic energy. And both times, if you make your mass bigger, then you have more energy. More mass means more energy. All right, and that's all I got. Hope you guys do all right on your homework. Hope that goes well for you. I try to make it all line up real nice for you. But if you have any questions, please feel free to email me. I'm checking it as often as I can. So absolutely, 100%. If you have a question, please email me, and we'll try and help you out. Okay? Have a good one, everybody.